rotational and translational collisions. You have to think about linear and angular momentum separately. Okay, so the angular momentum of the rod weights system turned into linear momentum of the weights, right? Referencing the last example. Angular momentum L equals I times omega, and linear momentum P equals mv are totally different quantities. L cannot turn into P, and P cannot turn into L. L becomes L. So what's happening here is the initial angular momentum of the rod weight system changes into the final angular momentum of just the rod plus the angular momentum of the weights. We're using angular momentum equals L equals m times v times r of the weights because now those weights are translating. Now they're moving linearly. So we have to use this version. While the rod is rotating, we can use I times omega. While those things are translating, we use that form of the equation. We can combine these two different forms because they're both just angular momentum. So you can have the two in the same equation. That's absolutely fine. As long as your angular momentum in the beginning equals all of your angular momentums in the end, or all of your angular momentums in the beginning equal all of your angular momentums in the end. The 2 is here because there's two weights carrying off angular momentum. That's why. L only turns into other L. In this animation, the equation becomes angular momentum in the beginning plus all of the angular momentums in the end. Negative because opposite direction. In this instance, I know I talked to you before, normally we take counterclockwise to be positive. This instance, just taking it to be negative. You can obviously switch those in. Hopefully by now, in this point of the year, you're comfortable with changing signs and realize that that negative is important, but where you use it is up to you. And it all comes down to defining your coordinate system. Pinball. This animation shows identical rods, red, green, blue, pivoted, brown, around the brown circle at the top. So there's a circle at the top, if you can't see it, and that's the pivot point. We're assuming no friction, no gravity, no friction. Identical bullets strike and stick to the rods, but note the bullets hit each rod at different points from the rod. The blue rod rotates faster than the green, which rotates faster than the red. Considering one of these three cases, let m be the mass of the bullet and v be the bullet's speed before striking the rod. The rod's rotational inertia is I. The bullet strikes the rod at a distance r from the axis, so r is small for the red and large for the blue. Initially, the angular momentum is carried by the bullet, L equals m times v times r. Afterward, the bullet is stuck into the rod, so the bullet's rotational inertia is adding to the rod's rotational inertia. We're using mr squared because all of the bullet's mass is a distance r from the rod's axis. So all of the angular momentum in the beginning has to equal all of your angular momentum in the end. In the beginning, we're using mvr because the bullet is translating. We have LF equals I times omega because the bullet rod system is rotating on its axis. And we're using total I, which is I plus mr squared, because we're using the rod and the bullet's rotational inertias together when they combine. And we get mvr, our initial angular momentum, equals I plus mr squared, which is the total moment of inertia, times our angular velocity in the end. Solving for angular velocity in the end, dividing out I plus mr squared on each side, and we get this nice looking equation. These animations assume the rod is much more massive than the bullet. This means that in the denominator, I is much higher than mr squared, giving us an approximation of the final angular velocity equals the mass of the bullet times the speed of the bullet from the distance that it lands from the axis divided by the moment of inertia for the rod. The bullet has a greater R from the axis along which the bullet moves for the blue rod, so the bullet has a greater angular momentum about the rod's axis in the blue case, because R is in the numerator. And if you have a bigger R, then you're going to end up with a greater angular velocity. The greater initial angular momentum for the bullet results in a greater final angular momentum in the blue case. Likewise, in the red case, R is smaller, the distance that the bullet lands from the axis, so that's smaller and it's in the numerator, which means angular velocity is going to be smaller. In all of the previous examples, angular momentum was conserved. However, linear momentum was not conserved. This is because the pivot itself exerts a force on the rod. The force of the pivot is an external force acting on the rod bullet system. So this external force changes the linear momentum of the system. Linear momentum is not conserved. The force of the pivot acts directly on the axis, so this force produces no torque. No torque means angular momentum cannot change, so the rod bullet angular momentum remained constant. These rods are pivoted at the center. Pretend you're looking down on the rods as they're pivoted on a frictionless surface. So we're not accounting for gravity, air resistance, none of that. The red bullets carry no angular momentum. So the red doesn't rotate after the collision. Blue's bullet carries more angular momentum because it is a greater distance from the axis. So the blue rod will rotate more. However, in all three cases, linear momentum is not conserved. The initial linear momentum is to the right because all three bullets are moving to the right. The final linear momentum is 0 because the centers of mass of the three systems are not moving. Linear momentum is not conserved because each pivot exerts an external force on the system. So don't come yelling at me, telling me I was wrong, you told me momentum is always conserved in all collisions. Yes, momentum is always conserved unless you have an outside, the external, unbalanced force acting on the system. And that's what we have here. So the axis itself is applying a force. That's why it's able to rotate about that point, because there has to be a force that's being applied at that point by whatever the pivot point is, the hinge, if you want. Now, if we take away the pivots, the rods are going to rotate exactly like they did before because the angular momentum of each system is exactly the same as before. But now the centers of mass move to the right because the rightward linear momentum before becomes rightward linear momentum after.